Good evening, sir.
Yes, ma'am. Shall I start, ma'am? Or will you have to wait?
Yes, sir, you can start.
Okay. So today's class we'll have to go fast and finish off with the synopsis of maximum chapters possible. All right. So we'll learn the important topics, important concepts which you have to remember, important formulas which you have to remember, so that you can answer the questions in your competitive exams. So we will try to learn the synopsis of certain chapters today, possibly a few chapters. The first chapter we will talk about the solids. In solids, what is that you're supposed to know? Now, in NEET, they say there is no questions asked based on the chapter solids, but you should know they can ask questions because in the NCERT, there is a chapter called as solids. We learn solids in NCERT. So there can be a question asked. Solids is a state of matter in which the particles are held together through a strong force of attraction. We have two types of solids. We know that it is amorphous and 1 minute. Crystalline solids, right? Amorphous and crystalline solid. Now you know the difference. You would have learned the difference in detail. So one of the difference we should know is crystalline solids are anisotropic. Crystalline solids and
Ani, you want me? Akka? Aya?
then Lakshmi, mute your phone. Mute your phone. Yeah, thank you. So amorphous solids are isotropic in nature. Physical properties will be same in all the directions. Crystalline solids are anisotropic. So this is the major difference. Otherwise, we know that amorphous solids have a range in melting point. Crystalline solids have a sharp melting point. Amorphous solids are called as a pseudo-solid, false solid, and crystalline solids are called as a true solid. Amorphous solids, they do not have definite geometry. Crystalline solids, they have definite geometry. And crystalline solids are further classified into molecular solids. In molecular solids, the particles are molecules. We have ionic solids. We have covalent solids. And we have metallic solids. So crystalline solids are classified into 4: molecular solids and ionic solids, covalent solids, and metallic solids. In molecular solids, the particles are molecules. And these molecular solids are of two types. One is a polar molecular solid. The other one is a non-polar molecular solid. So polar molecular solid means molecules which are having a polarity. Now, for an example, for a non-polar molecular solid, we will have example sulfur dioxide. We can have ammonia. All these are examples for polar molecular, non-polar molecular solid. For non-polar molecular solid, hydrogen, chlorine, Dry ice, carbon dioxide. Dry ice is carbon dioxide. All these are examples for molecular solid, which is non-polar. Now, ionic solids, we know that the molecules, the particles are ions here, and they are held together by ionic bond or an electrostatic force of attraction. And examples is NaCl, NaBr, KCl, KBr, goes on. So many examples can be given for ionic solids. In case of covalent solid, the particles are atoms. Particles are atoms. So these atoms are held together by a covalent bond. So example for a covalent crystals or covalent solid is silicon carbide, silicon dioxide, sand, silica. We can talk about diamond. Diamond is also an example for a covalent solid. Graphite is an example for covalent solid. Graphite. So all these are examples for covalent solid. Next, we have metallic solid. In case of metallic solid, the particles are metal ions. Particles are metal ions. These metal ions are called as kernels. Always metal will have positive charge. This positive charge metal ions are called as kernels. These kernels are held together by a force of CF electrons. Therefore, they are held together by a metallic bond. Example for metallic solids: any pure metal, copper, zinc, silver, gold, iron, etc. can be given as an example of metallic solids. They are malleable. Metallic solids are malleable, ductile. They are lustrous. They are insoluble in water. They have excellent thermal conductivity. These metallic solids have excellent thermal conductivity. They have high melting point. They are they are good conductors of electricity. Electric conductors. They are malleable. They are ductile. They are lustrous. So these are the examples with respect to the crystalline solid and the classification of crystalline solid. Now, there are 7 types of crystal systems. This is very important. Types of crystal systems. How many types of crystal systems? There are 7 types of crystal systems. Now, what are the 7 types of crystal systems? One will be called as cubic crystal system. The second one is tetragonal crystal system, hexagonal crystal system, rhombohedral crystal system, orthorhombic crystal system, monoclinic crystal system, and we have triclinic crystal system. There are 7 types of crystal systems, and you should remember the 7 types of crystal systems, and we have 14 types of Bravais lattice. 14 types of Bravais lattice. You can refer your material to know the types of crystal systems and also to know the 14 types of Bravais lattices. This is important. Bravais lattices. Now, in our syllabus, we have learned only a cubic system. We are not learning any other system. In case of cubic system, we have learned simple cubic lattice, body-centered cubic lattice, face-centered cubic lattice, all that we have learned. The number of particles contributed by simple cubic lattice, 3 problems your teachers would have taught you. That is 1. And the number of particles occupied by a body-centered cubic lattice is 2. And number of particles of contribution for a face-centered cubic lattice will be 4. So that problems I'm not going to teach you now. All right, so we will learn the other concepts, the formulas which you require to know in order to work the problems based on solids. Just give me a moment. All right. Now, in case of the simple cubic system, we should know to calculate the packing efficiency. How do we calculate the packing efficiency? We know that packing efficiency is calculated by the formula. Before that packing efficiency, we need to understand the types of the simple cubic crystals. One is simple cubic crystal. The simple cubic crystal is represented as SC. The simple cubic crystal, a cube will have only particles at the corners. Whenever the particles means it can have molecules, it can be atoms, it can be ions. This is the representation of simple cubic lattice. For a simple cubic lattice, now A is called as the edge length. A is called as, now the formulas we are going to learn, it is important. So A is called as the edge length, and R will be called as the radius. For a simple cubic lattice, the edge length is related to radius by the relation A is equal to 2R. A is equal to 2R. Since A is equal to 2, this relation you should remember, or we can calculate radius is nothing but A by 2, edge length by 2. This is for simple cubic lattice. And for a simple cubic lattice, the packing efficiency is volume of the sphere divided by volume of the unit cell. So volume of the sphere by volume of the unit cell into 100. If it's in percentage, it's 100. So it will be 52.4% in case of simple cubic lattice. The second we have is face-centered cubic lattice. In face-centered cubic lattice, we have a cube. We have a cube, and there are particles at the corners of the cube, and also there will be particles at the center of each face. A cube has 6 faces. So if this is one face, if you're sitting in a class, in a room, assume that a roof is one face, 4 walls is one face, and also the ground, what we are sitting on, that will be another face. So 6 faces we have. So in the center of 6 faces, you will have particles. One face is facing you and one face is behind you. So totally 14 the lattice points we have. Lattice points. So in case of simple cube, we have only 8 lattice points because we have only particles at the corners. In case of face-centered cubic, we have 14 lattice points. Now, what is the relation between radius and edge length? The relation between radius and edge length, you should remember, A is the edge length and radius is represented by letter A. Root 2A will be equal to 4R. Root 2A, I'm not going to teach you all that. So the only relations we're going to learn now because of the lack of time. Or why I'm talking about this, they can ask you to calculate the edge length or the radius. Or we can write A is equal to 4R by root 2. 4R by root 2. Or we can also write this as R is equal to A by 2 root 2. So these relations you should remember. Relation between radius and the edge length in case of face-centered cubic lattice. So for face-centered cubic lattice, the packing efficiency is volume of the sphere into 4, because number of particles occupied by contribution by in face-centered is 4 divided by volume of unit cell into 100. This will give you 74% packing efficiency, 74% or 74.2%. Now, next we have is body-centered cubic lattice. In case of body-centered cubic lattice, we have a cube and the particles are not only at the corner of the cube, but also at the center of the cube, only one particle. So lattice points, there are 9 lattice points, 8 in the corner and 1 at the center. Now, how is the radius and edge length related? The edge length and radius are related by the formula root 3A is equal to 4R. Root 3A is equal to 4R. Or we can write A is equal to 4R by root 3. Or we can write R is equal to root 3 by root 3 into A by 4. Rearranging the terms. So packing efficiency in the body-centered cubic lattice is 68%. 68%. I want you people to remember these formulas, these 3 formulas you can remember to work out the problems in case of the solids chapter. Now, we are not going to learn, and also one more formula we need to understand is to calculate the density of a matter, solid. Now, in order to calculate the density, the formula, what they will be, or what we are supposed to use is density is represented by letter rho. It's represented by letter rho. Density is equal to Z into M divided by NA into A cube. Z is the number of particles. Number of particles. Remember, for simple cube, the number of particles Z is equal to 1. For body-centered cubic lattice, Z is equal to 2. And for face-centered cubic lattice, Z is equal to 4. You should remember this. M is the molecular mass. M is the molecular mass. Na is the Avogadro number. A is the edge length. Edge length per cube. So A is edge length. So this formula you should remember in order to calculate the density of a solid. Now, these are the formulas which you have to remember in order to work out some problems based on the chapter solids. And you know crystal defects. Now, crystal defects, we have stoichiometric defect, non-stoichiometric defect. In that, you know Schottky defect, and also, you know, Frenkel defect, metal excess defect, all that. Theoretical part you have learned. Magnetic properties of solids, paramagnetic, diamagnetic, ferromagnetic, antiferromagnetic, all that, you know, it's a theory part. So, you know, you should know all that, revise. Now, in the chapter solids, if you have any clarification, you can ask me. If you can ask me any question you want to know, you can ask me so that we can solve. Quickly, anybody has any clarification? This is with respect to the solids chapter, the synopsis, what you're supposed to know in the chapter solids. Now, coming to the next chapter, that is, where is that gone? That is solutions. Solutions. We should know what is a solution. A solution is a combination of two or more components. A homogeneous mixture of two or more components will be called as a solution. And we are talking about only a binary solution. Binary solution means a solution contains only two components. Now, for an example, before that, maybe I forgot to talk about one concept in case of solids, that is a radius ratio. Radius ratio we are not learning, but you should know what is radius ratio. Radius of cation to radius of anion is called as radius ratio. The radius ratio will be always less than 1. So radius ratio will be always less than 1 because anions are larger in size compared to cations. Since anions are larger in size compared to cations, radius ratio will be always less than 1. This also maybe, this you can refer into, okay, radius ratio. I'll give you this radius ratio. This is important. The radius ratio, coordination number, crystal shape. The geometry can be determined by the radius ratio and also the examples, few of the examples. The radius ratio is between 0.155 to 0.225. Then the coordination number is 3 and the shape of the molecule is planar triangle. Planar triangle. Example for this is boron trifluoride, B2O3, boron trioxide. If the ratio or radius ratio is between 0.225 to 0.414, coordination number is 4. When the coordination number is 4, the shape of the crystal is tetrahedral. Example, zinc sulfide, mercuric sulfide. If the radius ratio is between 0.414 to 0.732, coordination number is 6. When the coordination number is 6, it's called as octahedral geometry, and you have sodium chloride, potassium bromide as an example. If the radius ratio is between 0.73 to 1.0, the coordination number is 8. And the coordination number is 8, the crystal will have body-centered cubic structure. Cesium chloride is an example. Titanium chloride is an example. So radius ratio is very important. Radius ratio, based on the radius ratio, we can predict the geometry, crystal shape of the solid. This is with respect to the solids. Now, coming to the solutions. Before we talk about the solutions, I'll erase this. Solutions, as I was defining, it is a combination, homogeneous mixture of two or more components. Now, for an example, salt in water. Salt in water will be called a salt to solution. When you add salt in water, salt will completely dissolve in water, and that salt solution will just appear like water. Therefore, that salt solution appears as one component. Those kind of solutions are called as homogeneous solution. Even though we have two or three components, and if it appears to be like a single component, then we call that as a homogeneous solution. So a mixture of two or more components, homogeneous mixture of two or more components will be called as a solution. Now, into this, we are talking about a solution, only a binary solution. In order to understand the solution, but express the concentration of the solution, we can express concentration in many terms, many ways. One is molarity. See, based on these problems can be asked. Basics of chemistry, they can ask you molarity. I'm not going to define molarity. Molarity is given by the capital formula. How do you calculate molarity? Molarity is calculated by the formula weight in grams divided by molecular mass into 1000 divided by volume of the solution. If they give you sodium chloride, for an example, if they give you 29 grams, 29.25 grams of sodium chloride in 100 ml, what is the molarity if they ask you? So 29.25 is the mass they've given. What is the molecular mass of sodium chloride? 23 plus 35.5. It will be 58.5. So 29.25 divided by 58.5 into 1000 divided by what's the volume they've given? They've given 100. On simplification, you will get the molarity. So remember these formulas. Likewise, normality. Normality is represented by letter M. Normality is given by the formula weight in grams divided by equivalent weight. Equivalent weight into 1000 divided by volume of solution. So the only difference here is equivalent weight. When we take equivalent weight, then we get the normality. So same discussion, how do we calculate the equivalent weight? Equivalent weight can be calculated of an element. Is calculated by the formula atomic mass by valency. So equivalent weight of acid is calculated by the formula molecular weight divided by basicity. Basicity means number of replaceable hydrogen. Now, if you take HCl, the basicity is 1 because only this hydrogen can be replaced. If you take sulfuric acid, 2 hydrogen can be replaced. So therefore, the basicity is 2. Whenever we talk about an acid, we will talk about basicity. Likewise, when we talk about the equivalent mass of a base, is molecular mass divided by acidity. What is this acidity? Number of replaceable OH minus. So what is the acidity of NaOH? The acidity of NaOH is 1. If you take calcium hydroxide, the acidity of calcium hydroxide is 2 because we have 2 OH minus. So whenever we talk about a base, we have to talk about acidity. Whenever we talk about an acid, we have to talk about basicity. Now coming to the third method of expressing the concentration, we can express the concentration in terms of molality. In solutions, molality is the important concept, molality and mole fraction. So we're going to learn about molality and mole fraction in a few minutes' time. Now, molality is number of moles of solute dissolved in 1 kg of the solvent. So solvent has to be taken in terms of kgs. When solvent is taken in terms of kgs, then it is called as molality. Then the term we express is called as molality, M-O-L-A-L-I-T-Y. This is R-I-T-Y, this is L-I-T-Y. Molality is represented by small letter M. So molality is calculated by the formula number of moles of solute. Number of moles of solute divided by mass of the solvent in kilograms, in kgs. Number of moles of a solute divided by mass of the solvent in kgs. Now, for an example, now how do you calculate number of moles? Number of moles is calculated by the formula weight in grams by molecular mass. Number of moles. Now, for an example, if I say, if the question is asked, calculate the molality of a solution formed by dissolving maybe 5.85 grams of sodium chloride in 100 grams of water. This is the question. Calculate the molality of the solution formed by dissolving 5.85 grams of sodium chloride in 100 grams of water. So the first question, number of moles we have to find. Number of moles of sodium chloride. So number of moles of sodium chloride is 5.85, weight in grams divided by molecular mass. Molecular mass is 58.5. So it will be 0.1 mole. Now what will be the molality? 0.1 mole divided by 100 grams. See, mass of the solvent in kgs. 100 grams is, see, 1000 grams is 1 kg. So 100 grams will be how many kgs? So 100 into 1 divided by 1000, it will be 0.1 kg. So it divided by 0.1. So therefore, the molality of the solution will be 0.1 molal, M-O-L-A-L. So remember this formula. Now, the important way of expressing concentration in the chapter solution is mole fraction. So mole fraction is defined as the ratio of number of moles of a particular component divided by total number of moles. So mole fraction, how do we define? It's defined as the ratio of number of moles of a particular component divided by total number of moles. So I told you how do we calculate number of moles. Number of moles is calculated by the formula weight in grams by molecular mass. Now, for an example, binary solution, we will have two components. One will be a solute, the other one will be a solvent. So this is important in order to talk about Raoult's law and other colligative properties. Now, mole fraction. Now, how do you define mole fraction? It's defined as number of moles of a particular component divided by total number of moles. Number of moles of a particular component divided by total number of moles will give you mole fraction. Now, for an example, if we say number of moles of solute to be NB and number of moles of solvent to be ANA, then what is the mole fraction of solute? The mole fraction of solute will be number of moles of solute, it's NB. Number of moles of total number of moles, it's NB plus NA. Number of moles of solute plus number of moles of solvent. Likewise, what is the mole fraction of solvent? So number of moles of solvent is Na divided by what's the total number of moles of solvent? Na plus N. So this is the mole fraction of solvent and this is the mole fraction of solute. You know how to find the number of moles. We learned it in the previous slide, that is weight in grams by molecular mass. Generally, mole fraction is represented by letter X. X of solute and X of solvent we represent. So this is important. And you should remember mole fraction of solute plus mole fraction of solvent is always equal to 1. For a binary solution, mole fraction of solute plus mole fraction of solvent is always equal to 1. Now, the list of formulas I'm going to give you so that I'll write here itself. List of formulas which will be useful for you. Now, normality and volume relation. Normality, I told you how to calculate normality and volume relation. That is N1 V1 is equal to N2 V2. Normality of one solution into volume of one solution will be equal to normality into volume of the other solution. N1 V1 stands for representation. Likewise, the relation between molarity and volume. Molarity and volume. It is M1 V1 is equal to M2 V2, same type. and it is M1, molarity into volume of one solution will be equal to molarity into volume of the second solution. Normality of an acid, normality of acid. The third relation, normality of acid is equal to basicity into molarity. Basicity into molarity. So normality of a base, normality of a base will be equal to acidity into molarity. These are the formulas which you have to remember. Likewise, when two acids are mixed or two bases are mixed, what happens to the normality? So normality of a mixture will be equal to N1V1 plus N2V2 divided by V1 plus V2. Or we can write in terms of molarity. Molarity of a mixture will be equal to M1V1 plus M2V2 divided by V1 plus V2, total volume. This is the formula which we will be using when there is no reaction, when two acids are mixed or when two bases are mixed. But what happens if we mix an acid and a base? When we mix an acid and a base, reaction will take place. When we mix an acid and base, when the reaction takes place, then the corresponding mixture molarity will be M1V1 minus M2V2 divided by V1 plus V2. See, when it's a mixture of acid and a base, there is a minus because there is a chemical reaction taking place. But when there is only acids, two acids or two bases are mixed, then the formula what we'll be using is plus in both the cases. When there is one acid and one base, then there is a reaction, neutralization reaction taking place, and then you need to use a minus sign. These are the formulas which you have to remember. Basics of the formula, the chemistry formulas, so that we can work the colligative properties in detail. Now, you people are not asking any clarification. At least you can type if you are able to follow, or if you have any doubts, you can type and clarify your doubts. Right? At least you can acknowledge that you are understanding. Then it will be good for me to continue. The next is the colligative properties. Colligative property depends on the number of solute particles, not on the nature of the solute particles. You know all that, 4 colligative properties. You know that is relative lowering of vapor pressure, all that. Osmotic pressure, relative lowering of vapor pressure, elevation in boiling point, depression in freezing point, all that we know. Now, the formulas are now Henry's law you should know. Henry's law, the mathematical representation of Henry's law. So pressure will be equal to Kh into mole fraction. So this is Henry's law. This is the formula. Now, Henry's law states the partial pressure of a gas above the surface of the solution is directly proportional to mole fraction of the solution of the gas in the solution. So partial pressure of the gas on the surface is directly proportional to mole fraction of the gas. So if you remove the proportionality sign, they give a proportionality constant. The proportionality constant is called as Henry's constant, Kh. Henry's law constant. It is not constant for all. It depends on the gases. It varies with the nature of gases. Now coming to the Raoult's law. Now how do we define Raoult's law? Raoult's law is defined as mole fraction, or maybe we can write vapor pressure of a component in an ideal solution, or we can write vapor pressure of each liquid in a solution is equal to mole fraction of the solute and vapor pressure of the pure component. Now we can write mathematically the Raoult's law for a binary solution as vapor pressure of a solution or vapor pressure of each liquid will each liquid in a solution will be equal to mole fraction of the solute into the vapor pressure of a pure component, vapor pressure of a pure component. whereas P naught. We can write otherwise, if it is, we are talking about a solvent, we can write vapor pressure of a solute can be written as PB, solute is taken as B, that will be equal to mole fraction of the solute into partial pressure of the pure vapor pressure of pure solute. Now, what is the vapor pressure of a solvent? The vapor pressure of a solvent is equal to PA. A is represented as a solvent. PA will be equal to mole fraction of the solvent into P naught of A, vapor pressure of pure solvent. This is the mathematical representation of Raoult's law for a binary solution. Now, vapor pressure, I'm not defining. Vapor pressure is inversely proportional to boiling point. This relation you should remember. When vapor pressure is high, boiling point will be low. And boiling point, if it is high, it means vapor pressure is low. This relationship you should remember. Now, we also can represent Raoult's law by a formula. P naught minus P divided by P naught is equal to NB divided by NA plus NB. Now, what is this P naught minus P divided by P naught? It is called as relative lowering of vapor pressure. Relative lowering of vapor pressure is equal to mole fraction of the solute. This is one more way of defining Raoult's law. All right. So, what is the formula to calculate the relative lowering of vapor pressure? It's NB by NA plus NB. You know what is number of moles? How do you calculate number of moles? So that we know. Now, if a solution obeys Raoult's law at all conditions, then we call those kind of solutions to be an ideal solution. So, ideal solution, in case of ideal solution, delta H of mixing is equal to 0. That means when we mix two solutions, takes place, no heat is liberated or no heat is absorbed. Therefore, delta H, enthalpy of mixing, is 0. Likewise, then delta V of mixing is also 0. When we mix two solutions, there is no change in volume because there is no chemical reaction taking place. Therefore, delta V of mixing will also be 0. And the third point in case of ideal solution is interaction between solute, almost same as that of solute and solvent. So interaction, when the interaction between solute and solvent is same as the interaction between solute and solvent, they are called as ideal solution. Example for ideal solution, remember benzene and toluene. If you mix benzene and toluene, no chemical reaction takes place. Hexane and N-heptane, no chemical reactions taking place. Ethyl bromide and ethyl chloride, no chemical reaction, therefore ideal solution. Chlorobenzene, bromobenzene. These all are examples for ideal solution. So ideal solution is a solution which obeys Raoult's law at all conditions. For an ideal solution, the graph will be like this. Now, this, if we take a number of moles of a component, A is 1 and B is 0, and here A is 0 and number of moles of B is equal to 1. Here B is equal to 1. Then we will get a graph like this. This is the vapor pressure of B, and this will be the vapor pressure of A. And this will be the total vapor pressure. This will be the total vapor pressure. This will be the graph for a solution showing ideal behavior. Now, if we talk about a solution which shows a non-ideal behavior, a solution which does not obey Raoult's law at all conditions of temperature and pressure, will be called as a non-ideal solution. So for a non-ideal solution, there are two types of non-ideal solutions. What are the two types of non-ideal solution? A non-ideal solution showing positive deviation and a non-ideal solution showing negative deviation. So if a non-ideal solution means a solution which does not obey Raoult's law. Now, in case of a non-ideal solution, there are two types of non-ideal solution. Non-ideal solution showing positive deviation as well as non-ideal solution showing negative deviation. Now, positive deviation, a non-ideal solution showing this is non-ideal. Positive deviation and a non-ideal solution showing negative deviation. Now, in case of a solution, in case of a non-ideal solution showing positive deviation, delta H of mixing will be greater than 0. That is, delta H of mixing will be positive. It's an endothermic process. Likewise, delta V of mixing will be greater than 0. It will be positive. That means the volume will increase. When two solutions are mixed, the volume will increase. And the third difference is solute-solvent interaction is weaker than solute-solute interaction and solvent-to-solvent interaction. So these are the these are these points in case of a solution which is showing a positive deviation. Now, in case of the graphical representation, this is for an ideal solution. So in case of a non-ideal solution showing positive deviation, what happens is the graph will be like this. There will be increase. So vapor pressure, this red line indicates a solution showing positive deviation. Now coming to a solution which shows negative deviation. A solution which shows negative deviation, it will be an exothermic reaction. Delta H of mixing will be less than 0. It is negative. Less than 0 means negative. Volume of mixing will be less than 0. It is also negative. That means solute-solvent interaction will be greater than solute-solute interaction. And that will be greater and water solvent-solvent interaction. In case of a non-ideal solution showing negative deviation, what happens is the graph, what I'm going to draw, will look a little complex, but we will try to draw it. I don't want to write it. See, this yellow line stands for an ideal solution. The red line shows for a non-ideal solution showing positive deviation. This green line shows a graph of a non-ideal solution excuse me, showing negative deviation. This green. So it's 3 different graphs. I've put it in one. A solution showing a non-ideal deviation. Examples: acid and water, HCl and water, nitric acid and water, chloroform and water. All these are the solutions which shows negative deviation. Now, acetone and ethanol, ethanol and water, all these are solutions showing carbon disulfide and acetone, all these are solutions which shows a non-ideal solution showing positive deviation. Coming to the formula to calculate the relationships, I'll give you the relationship for different colligative properties, and we will see what can be done next. So one of the formula I gave you to calculate relative lowering of vapor pressure. We can calculate relative lowering of vapor pressure. Molecular mass we can calculate using the relative lowering of vapor pressure. Now, coming to the formula, list of formulas, what you're supposed to know in this chapter is number of moles. I told you how to calculate, and I told you P naught minus P divided by P naught is equal to NB divided by NA plus NB. Since NB is very small, we can neglect this. We can write P naught minus P divided by P naught is equal to NB by NA. And we know that P naught minus P divided by P naught is equal to WB by N molecular ND divided by WB divided by NMA, weight in grams by molecular mass. So this formula reduces to P naught minus P divided by P naught is equal to WB into MA divided by W A. This is A, right? Sorry, this is A. This is A into MB. This formula you should know. MB is the molecular mass of the solute. All these values will be given and they'll ask you to calculate the molecular mass. So this is based on Raoult's law. Now coming to the problems based on the formula based on elevation in boiling point. Elevation in boiling point is also called as ubilioscopy. Elevation in boiling point is represented by delta TB. So delta TB is given mathematically by delta TB is the elevation in boiling point is T minus TB. T is boiling point of a solution. T is boiling point of a solution. TB is boiling point of a pure solvent. Pure solvent. Remember, boiling point of a solution will be greater. So delta TB is directly proportional to molality. So delta TB is equal to Kb into molality. Kb is called as molar elevation constant. We can calculate delta TB by the formula 1000 into Kb into Wb, weight of the solute, divided by Mb, molecular mass of the solute, into Wa. A is a solvent. Likewise, the depression in freezing point. The next colligative property is depression in freezing point. Depression in freezing point is also called as cryoscopy. It's represented as delta TF. So delta TF will be reverse of this. It'll be freezing point of a pure solvent minus freezing point of a solution. So the relation delta TF is proportional to molality. Delta TF will be equal to Kf into molality. Kf is called as cryoscopic constant. It's a constant. So delta TF is calculated by the formula 1000 into Kb into Wb, Kf into Mb into Wa. Same formula, but it is Kf and Kb. Now coming to the next colligative property is called as osmotic pressure. Now osmotic pressure, you know what is osmosis, and osmotic pressure is calculated by the formula pi V is equal to EnRT, or pi V is equal to W2 by AM2 into RT. W2 is solute. So, or we can write pi is equal to W2 into RT divided by V into M2. These are the formulas which you're supposed to know. And also we can write pi V is equal to pi is equal to C into RT. C is concentration, because if we write pi is equal to N by V RT, we can write as per this equation B, I can take it down. This N by V is nothing but concentration. So pi is equal to C into RT. So these are the formulas which you're supposed to know in order to work out some of the problems in the chapter solutions. And you should know what is the reverse osmosis, and you should know what is hypertonic, hypotonic and isotonic solutions. With examples you should know. This is with respect to the chapter solutions. And the last part of the chapter solutions, we have something called as Van't-Hoff factor. I'll give you one or two formulas so that the chapter is complete. So the Van't-Hoff factor. Van't-Hoff factor is represented by letter I, Van't-Hoff factor. Now, Van't-Hoff factor, a solute can undergo dissociation or association. That can be determined by a factor called as a Van't-Hoff factor. This Van't-Hoff factor I is given by theoretical molecular mass by experimental molecular mass. Theoretical molecular mass by experimental molecular mass will give you Van 't Hoff factor. If a solution is undergoing dissociation, if a solute is undergoing dissociation, then the degree of dissociation alpha is given by the formula I minus 1 divided by n minus 1. I is Van 't Hoff factor. If a solute is undergoing association, a solute can combine, then alpha is given by the formula 1 minus I divided by 1 minus 1 by n. N is the number of particles. How do we calculate the number of particles? Number of particles, now for an example, number of particles can be calculated by knowing the dissociation pattern. Now, for an example, if you take urea will not dissociate in water. Therefore, I is equal to 1. If you take NaCl will dissociate to water from Na plus and Cl minus. So, I is 2. And Van 't Hoff factor for barium chloride, if you take barium chloride, you get barium ion and 2Cl minus ion. Therefore, Van 't Hoff factor will be 3. So, number of ions will give you Van 't Hoff factor. And remember, if I is equal to 1, no association nor dissociation. The solute will not undergo association nor dissociation. If I is greater than 1, then the solute will undergo dissociation. And if I is less than 1, the solute will undergo association. These are the formulas which you have to remember in the chapter solution. Right? So we'll work out some of the chapters later in the next class. Ma'am, I'll stop the class, ma'am. Thank you.